presentation. It is joint work with my colleague Taha. I thank the organizer to program this presentation at the beginning, because it's the beginning of hydrologic statistics, of frequency analysis. So I'm presenting multivariate descriptive analysis with depth functions. So the context, we know that frequency analysis is a commonly used procedure for the prediction of extreme hydrologic events such as floods, storms, and droughts. And what Taha mentioned before, that generally several correlated characteristics are used to describe correctly hydrological events. The example we see here is the flood, which is described through its volume, peak, and the duration, among other features. You see, for example, from the STAHI website, that there is a lot of papers with multivariate frequency analysis, especially with using copula. And frequency analysis is two parts: is the univariate and the multivariate. The univariate one, we focus only on one variable, for example, and especially is the peak. And in the multivariate one, we have a lot of features. For example, the volume, the duration, and the peak all together. The main steps of hydrological frequency analysis, I try to put them in four main steps. The first one is to exploratory analysis of the data. The second step is testing the assumptions. And the third one is the modeling. And the last one, which is the result of all those, is the risk assessment. Now I'm going to detail each one of these steps. The first one is the exploratory. We are interested in to visualize data, to evaluate location, scale, skewness, curves, outliers, and all this stuff. The second step is testing, which Taha already mentioned it. We have to check homogeneity, stationarity, and independence. And then we are going to modeling. We are going to fit a distribution or a copula and estimating the corresponding parameters. And by doing all this, we come to the last step, which is risk assessment through return per risk or quantiles. So today I'm focusing only on the first step, which is exploratory analysis. In the univariate setting, there is a large literature, it's very simple, and it's widely used. However, in the multivariate setting, the first step is not considered at all. There is a very, very sparse literature. It's not easy to use. And it's not available, the tools are not available. And this is the aim of my presentation. The testing part is generally not considered. If we not consider what I presented earlier. However, the modeling step, is the most studied, especially because of copula. And the risk assessment is starting to be studied relatively in a lot of papers. So the first step is exploratory analysis. So why it is important? So it allows to base the inference on the right data. This is the first thing. If the data we find that the data are appropriate or good quality, so we can go further for other analysis. And it allows also to understand the nature of the phenomenon before going to the modeling. And it is also useful to have an idea, a prior idea about the model before going to testing and it also guides the selection of the distribution and the shape and summarize the statistics. So this is why this step is important. So because it's important, why it is not considered? So first of all, because there is not appropriate tools. They are not available. They are not available in a clear and practical way. what is available is only classical statistics, classical multivariate tools, which are simply the analogous to the multivariate ones, which is particularly component-wise. We are considering both the variables, but like separately, each component itself. The second problem with the classical multivariate techniques, they are moment-based. They are based on the variance, the skewness, the moments. Sometimes these moments don't exist. And the problem also, all people focus on the modeling, which is especially because of the fashion of copula. It attracts a lot of attention, so we are forgetting the first steps. So the alternative, now what we are proposing, there are depth-based techniques. So with these techniques, we try to avoid the above drawbacks. They are not we are avoiding the component-wise. They are moment-free, and generally they are fine invariant. A fine invariant is useful, for example, when you change the scale, when you transform your variables, simple transformation. This is very useful. And it is moment-free, so it exists always. And it is not component-wise, which is very, very important. So the main tool is the depth functions. So what's the depth functions? What you need really to know is that depth functions is an intelligent or a geometric way to order multivariate observations. So we are in the multivariate setting, and we want to order the data. And one of the well-known applications is the definition of the median, multivariate median, which is the deepest point. One of the good examples of depth functions is the Mahalanobis depth functions, which is simply a transformation of the Mahalanobis distance. So this gives the idea that all distance we know are special cases of depth functions. And there is other depth functions which are not distance-based, which is for example, the half space depth functions, which is presented here. For example, if I want to evaluate the depth value of the theta, the point theta, so I'm going to trace different half spaces, lines here, and to compute the number of points observations in the two sides of the half space. And I'm taking the minimum. I'm doing this around all the data. I'm taking the minimum of the minimums. And this is the depth value of theta. So I'm going back now to our step exploratory analysis. So it's composed of different steps or parts, and each part is also composed of different elements. For example, for visualization, you can use direct or direct ways. The location, which evaluates the centrality, it can be done with mean, median, or trimmed means. The scale, which measures the dispersion of the data. There is matrix or curves, through matrix or curves. The skewness. It's not like in the univariate case, we can say only the data is symmetric or not. In the multivariate case, it's very different. It's spherical, asymmetric, or elliptic, or antipodal, or angular. There is not one way to evaluate symmetry. And also, the curve is through the bigness. And the last point is outliers. So all these points are in the first step, which are ignored. For applications, I didn't introduce all the definitions, so there's no time for this, because I have only 15 minutes. So we considered floods through their peak volume and duration, 3 couples, 2 case studies from Quebec. In the first case study, we treated all all the parts. For the second case study, we focused only on outliers. So the visualization. So the first one is what we call the backplot position, backplot, which is simply a generalization of what is in the univariate box plot. So we see that all three series are unimodal, and there is a positive dependent for the first two couples, which is QV and DV, and there is no clear dependence for the last one, the peak and duration. For the contours, we see that QD, the last one, is more circular, and the contours are more close to each other compared to the two first ones. The location. You see the first line is the location parameters in the data, and in the second row is a zoom. But we can see that generally all location parameters are located in the center, which is expected, and the mean, which is the red ones, are generally influenced by the extreme values of the sample, which is not the case of the median of the median. About scale, so we can evaluate it by as a matrix or curves. With matrix, so all values of the covariance matrix are positive. We see that those of volume and peak are larger than those of the other ones, and all the values are positive except some of the Q and D. And if you see also the scale in terms of as a curve, this curve is based on depth functions. So we see that QV, the first one, is more dispersed than the others, and the variability, this is because of the variability in D, induced by the duration, is already included in the peak and volume, because the peak and the volume are already evaluated on this duration. But the point is that all these findings are confirmed, are already revealed by the bug plots and the visualization. What about now the skewness? Here is the spherical skewness, and the other side is the elliptical skewness. These curves are also based on depth functions, and the closer the curve to the diagonal, the data is more symmetric. So we can see that the sample DV is very close to spherical symmetry, the one in the middle. And in the other one, all distributions are more likely to be elliptical. And this is this result is also confirmed by the backplots. So in backplot, we only see that there is some symmetry, but here we are confirming this result. There is also other skewness, the antipodal and the angular. For the antipodal skewness, all series seem to be symmetric because they are already elliptical. For the angular, it's only QD which is angular. QD is the last one. And the conclusion of all the symmetric studies, all the series are elliptical symmetric. Are elliptical. And what we can see here, that gives us the idea that we can consider for modeling meta-elliptical distributions. And what I can say for the same data exactly, they are modeled by Gamble, which I think it's not meta-elliptical distribution. So because we didn't perform this analysis, so we should do this analysis before modeling. So now for the cortices. So the series QV. Look, here, there is two ways to evaluate the cortices. The series QUV represent the most peaked sample, the first one, because the curve is very close to the diagonal. So overall, QV is the most peaked series using the L star. This is how we measure it. And the appropriate distribution should be highly tailed as expected. Because we know by treating the extremes, the data should be highly tailed. So here we are confirming this. One will just imagine it. So I'm finishing for the conclusion very quickly. So the techniques and methods presented here, which are depth-based, are considered the first step before any modeling or testing, and it includes several features: location, scales, units, curtains, outlier detection. And the depth-based methods are shown to be superior to other classical methods. And this preliminary step of the analysis is very useful for modeling and risk evaluation. It allows to screen the data, to guide the selection of the appropriate distribution, and to compare samples. Here we compared three couples. And in terms of results, specific results, the first case study shows that we don't find outliers, and the data are to be elliptically symmetric and heavy-tailed. The second case study, we find some outliers, but by checking we find that they are really observed. We cannot remove them. So we have to consider in the modeling part robust models. We cannot consider any model because there is outliers and we cannot remove them, so we have to consider robust models. So I'm finished with this, so thank you very much.
Any question? Regression. Regression is more applied than 2 or 3 dimensional variables. But going to the point, it is very bad to have the good memory, but it was just my doctoral degree 48 years ago when I used multiply analysis for flat hydrographs. And it was just the time, the beginning of the computers, so I had to use some statistical tables of Owen. The idea was just to translate all marginal distribution to the normal distribution, and then hypothesis that if all distribution are marginal distribution are normal, then the multidimensional distribution is normal as well. And I did like that. So sorry for remember you. Okay, I can also remember that it was, I think, in 1975 that 3 or 4 of us, one was Professor Une, the second was Seleshi Nodge, it was me and maybe Mark Moore. We came to the conclusion that it is about time to separate statistics from IHS, and then it was just the beginning of this Journal of Stochastic Hydrology and Hydrology and Hydraulics, which were, I think, a lot of years it was before it was transformed in this environmental one. So, I mean, we should keep in the account that, say, 40 years ago or 30 years ago, this idea failed and is reborn again. Thank you.
So it was just a comment, I didn't see a question.